I wanted to talk a little bit about this lab. This lab, the motion lab, you're going to be doing some analysis of motion. There's three parts. The first part is constant velocity. You're going to be looking at a video and determining what that velocity is. This part two deals with average acceleration, figuring out the average acceleration and using that to make a prediction. And then part three deals with what the predicted value of the acceleration should be and how that compares to the measured value. Now, for all of these, something else that we're taking into account is uncertainty. There is no such thing as a perfect measurement. There is always some uncertainty in our measurement, and we want to take that into account. And you're going to be making estimates of what the uncertainty is and also doing calculations. So let's take a look at the first part. So here's part one. And in the video here, you can see there goes the puck. It's going down. And these arcs that you see here, let me make this a little bigger. These arcs are all 0.5 meters apart. And so you want to note at which frame the puck, the center of the puck, hits these arcs. Okay, now the frame count, when the frame at frame 0, the puck is at the origin. Okay. So here it is at frame 64, and you can see it hasn't quite hit the red arc. And if I go really quick, oops, didn't go quick enough there. Let me back it up a little. I am terrible at this. There we go. Okay. So here you can see at frame 26, it hasn't quite hit the red arc, the second red arc. And I know that at frame 27, it actually ends up just slightly past. And so the question is, do you put down frame 26 or do you put down frame 27? Can't put down in between. It has to be one or the other. And so you must pick, but there's uncertainty because that's not actually when it hit that particular arc. So you will put down in this green table at what frame it hit each arc. Okay. Then down here in this blue table, you need to put in the uncertainty of your frames, of your frame measurement. By how much do you think you could be off? Now, when you state what frame it's at the individual arcs, that has to be an integer, but the uncertainty, that could be a fraction. It doesn't have to be an integer. It's an estimate by you, and to a certain extent, it's a matter of opinion. But there are some things that are clearly unreasonable as uncertainties. For example, you're not going to be off by 10 frames. Okay, this is not going to be frame 26 plus or minus 10 frames. That is completely unreasonable. At the same time, you can't be too small. So you can't be too big, you can't be too small. The general kind of rule of thumb for the range is you would never be twice the smallest increment that you have as your measuring tool. You'd never be more than twice for your uncertainty, and not for your estimated uncertainty anyway that we're doing here. And you would never be less than a tenth. That doesn't mean that a tenth of the smallest increment is okay. It depends on the situation. And that also doesn't mean that twice the smallest increment is okay. Again, it depends on the situation. But, outside of those, smaller than a tenth of an increment or of the smallest increment, or twice the smallest increment, more than twice, I should say, those are unreasonable uncertainties. So we wouldn't make those choices. Anyways, so you'll put down what you think the uncertainty is, and there's a range of values that's accepted. Then you have to put the frame that reaches the fifth arc. You've actually already done this in the green. It was the last entry in the green table. Okay. From that frame, you should figure out how long it took to get to the fifth arc. You can do this because you know that it states it right there in the video and also up above in the red. It states that it took 30 frames per second. This was filmed at 30 frames per second, so you can use that to determine the elapsed time. The distance there, delta r to the fifth arc, you can see in the green frame, the green table, we've already mentioned what the distances are. The uncertainty there, you can figure that out. It mentions it in the blurb that this is simply 5 times the stated grid spacing uncertainty in the video, which is clearly stated. That grid spacing uncertainty is mentioned there in the video. You should be able to calculate speed because you know your displacement of your time and it's going at a constant speed here. And then you can use the formula below the table to calculate the uncertainty. You also can get the angle from the video. You can see the protractor there in the video. So you can get the angle and then you can use vector analysis to figure out the x component of the velocity and the y component of the velocity. And you can compare that to what kinematics predicts because this video goes through twice. If I hit play and let it go, it'll start playing again here in just a minute. There it goes. And it's going to stop right there. And let me pause it as well. At frame 29, we can see it has moved. You can see it's right on that white vertical line. That white vertical line is an x displacement of 1 meter. So we know in 29 frames, its x displacement is 1 meter. So we can use that to figure out the x velocity using kinematics. And a similar thing happens, a similar thing happens, in just a moment it pauses there, then it continues to right there. That is a y displacement of 1 meter at frame 63, so we can use that to calculate the y velocity. Then come down here for part 2, the average acceleration. You've got this video of this guy on the cart. You'll notice in the video that if I hit play here, he's not moving at the beginning, and then he turns on the fire extinguisher and he starts moving across the floor. And so what you have to do is you have to, in the green table here, you have to identify the frame at which he starts moving, the uncertainty of that frame, the frame at which he hits 4 meters, the uncertainty of that frame, you can get the elapsed time, and use kinematics to figure out the average acceleration. You know the distance, it's going to be 4 meters, you know the initial velocity, and you know the elapsed time. You will have calculated the elapsed time by that point. So you can get the average acceleration and then use the formula below the table to calculate the uncertainty of your acceleration. Then you come here to the blue table, and now we're going to use that average acceleration to make a prediction. And the prediction is going to be at what frame does he hit 2 meters. Now we can look on the video and we can see at what frame he gets to 2 meters. He hasn't quite got there yet in mind. You can see at frame 73, he isn't quite at 2 meters, but he's close. So we can see from the video when he gets to 2 meters, and that's actually what you're going to put in the last box here in part 2. Okay. But we want to be able to use kinematics to predict what frame he would get to the 2 meter mark. And so what you have to do is use the use the acceleration you calculated already and use the kinematic formulas to calculate how long it would take him to go 2 meters. Use that elapsed time, figure out how many frames that would be. And then once you know how many frames it takes to go 2 meters, you know, back in the green table here, the initial frame at which he started moving, so you can figure out, you can predict at what frame he should get to 2 meters. And we calculate the uncertainty in that prediction using the formula below the table. And then you can calculate the minimum and maximum value for the predicted frame, for the predicted frame at which he'll get to 2 meters. And you're just doing that because, remember, uncertainty is always going to be a plus or minus. You know, this I measure the distance as 10 meters plus or minus 2 centimeters. You know, so use that plus or minus to figure out the max and min value. Then for part 3, this is a cart going down a ramp. And just like the guy on the cart, the motion here doesn't start at frame 0, so you have to figure out what frame the cart actually starts moving, and the uncertainty. And you want to find the frame at which it gets to the 70-meter mark. Then you'll get the elapsed time, use kinematics to get the average acceleration, use the formula there to calculate the uncertainty of the acceleration. This video was shot at 60 frames per second. So bear that in mind. Also bear in mind it only shows every other frame. So that plays into our uncertainty of the frames. Right? Instead of showing every frame, it's showing every other frame. I don't know why, but that's how they chose to do it. So you need to account for that in your uncertainty. The uncertainty of the frames, to be precise. Now, the thing is, this cart's going down a ramp. Let me play the video. You can see it's going down the ramp. Okay. Well, we can actually use Newton's second law to predict what the acceleration should be. And the formula is given here. It says the acceleration is g sine theta, where theta is the angle of inclination. G is just the free fall acceleration. That's 9.8 meters per square second. And so you can get the angle by using the protractor that's in the video there. State your uncertainty. You're estimating what your uncertainty is. Calculate the predicted value of the acceleration. Calculate the uncertainty of that predicted value. And then down here, you'll get the range for your average acceleration. That's from the green table, and the average, and the predicted acceleration from the blue table. And hopefully, ideally, those ranges should overlap. That's the idea. If you have any